Hello friends, in the previous lecture we discussed about the field effect transistors being unipolar devices having three terminals, namely source, drain and gate. The JFET operates with a reverse biased PN junction with high input resistance due to the reverse biased gate source junction. FET is called a square law device because of the relationship of ID to the square of a term containing VGS. In today's lecture, we shall discuss and analyze JFET biasing, describe self bias and the Q point of a self biased JFET, graphically analyze a self biased and voltage divider biased JFET, discuss Q point stability of JFET and finally talk about ohmic regions. JFET biasing. Using some of the JFET parameters discussed previously, you will now see how to DC bias JFETs. Just as with the BJT, the purpose of biasing is to select the proper DC gate to source voltage to establish a desired value of drain current and thus a proper Q point. Three types of bias are self biased, voltage divider bias and current source bias. Self bias. Self bias is the most common type of JFET bias. Recall that a JFET must be operated such that the gate source junction is always reverse biased. This condition requires a negative VGS for an N channel JFET and a positive VGS for a P channel JFET. This can be achieved using the self bias arrangement shown in figure here. The gate resistor RG does not affect the bias because it has essentially no voltage drop across it and therefore, the gate remains at 0 volt. RG is necessary only to force the gate to be at 0 volt and to isolate an AC signal from ground in amplifier applications. For the N channel JFET as shown in the figure, IS produces a voltage drop across RS and makes the source positive with respect to ground. Since IS is equal to ID and VG is equal to 0, then Vs is equal to ID into Rs. The gate to source voltage is then given by the following equation where VGS is equal to VG minus Vs is equal to 0 minus ID into Rs and is equal to minus ID into Rs. Thus, VGS is equal to minus ID into Rs. For the P channel JFET shown in part B of the figure, the current through Rs produces a negative voltage at the source, making the gate positive with respect to the source. Therefore, since Is is equal to ID, VGS becomes equal to positive ID into Rs. Keep in mind that analysis of the P channel JFET is the same except for the opposite polarity voltages. The drain voltage with respect to ground is determined as follows, where Vd is equal to Vdd minus Id into Rd. Since Vs is equal to Id into Rs, the drain to source voltage is Vds is equal to Vd minus Vs is equal to Vdd minus Id into Rd plus Rs. Setting the Q point of a self biased JFET. The basic approach to establishing a JFET bias point is to determine ID for a desired value of VGS or vice versa. Then calculate the required value of Rs using the following relationship. The vertical lines indicate an absolute value. Rs is equal to VGS over ID. For a desired value of VGS, ID can be determined in either of the ways, from the transfer characteristic curve for the particular JFET, or more practically from this equation where ID is approximately equal to IDSS into 1 minus VGS over VGS off whole squared. IDSS and VGS off values are taken from the JFET data sheet. The next two examples illustrate these procedures. Determine the value of Rs required to self-bias an n-channel JFET that has the transfer characteristic curve shown in the figure at VGS is equal to minus 5 volts. From the graph, ID is equal to 6.25 milliamperes when VGS is equal to minus 5 volts. So, Rs becomes equal to 5 volts divided by 6.25 milliamperes and comes out to be 800 ohms. In the second example, we are to determine the value of Rs required to self-bias a p-channel JFET with datasheet values of IDSS is equal to 25 milliamperes and VGS off is equal to 15 volts. VGS is to be 5 volts. In order to calculate ID, we use this equation where ID is approximately equal to IDSS into 1 minus VGS over VGS off whole squared. Substituting the values in given equation, we get ID approximately equal to 25 milliamperes into 1 minus 5 volts over 15 volts whole squared, and ID comes out to be 11.1 milliamperes. Now we determine Rs using the equation as given here, where Rs is equal to VGS over ID. Substituting the values, we get Rs equal to 450 ohms. Graphical analysis of a self-biased JFET. You can use the transfer characteristic curve of a JFET and certain parameters to determine the Q point of a self-biased circuit. A circuit and its transfer characteristic curve are shown here in this figure. To determine the Q point of the circuit, a self-biased DC load line is established on the graph as follows. First, calculate VGS when ID is equal to 0. VGS is equal to minus ID into Rs, and substituting the values, we get VGS equal to 0 volts. This establishes a point at the origin on the graph. Next, calculate VGS when ID is equal to IDSS. From the curve, we can see that IDSS is equal to 10 milliamperes. So, substituting the values in the equation VGS is equal to minus ID into Rs, we get VGS equal to minus 4.7 volts. This establishes a second point on the graph. Now, with 2 points, the AC load line can be drawn on the transfer characteristic curve as shown in this figure. The point where the load line intersects the transfer characteristic curve is the Q point of the circuit as shown, where ID is equal to 5.07 milliamperes and VGS is equal to minus 2.3 volt. For increased Q point stability, the value of Rs in the self bias circuit is increased and connected to a negative supply voltage. This is sometimes called dual supply bias. Voltage divider bias. An N-channel JFET with voltage divider bias is shown in the figure here. The voltage at the source of the JFET must be more positive than the voltage at the gate in order to keep the gate source junction reverse biased. The source voltage is given by this equation where Vs is equal to Id into Rs. The gate voltage is set by resistors R1 and R2 as expressed by the following equation using the voltage divider formula where Vg is equal to R2 over R1 plus R2 into Vdd. The gate to source voltage is Vgs is equal to Vg minus Vs and the source voltage is Vs equivalent to Vg minus Vgs. The drain current can be expressed as Id is equal to Vs over Rs. Substituting for Vs, Id comes out to be Vg minus Vgs over Rs. Graphical analysis of a JFET with voltage divider bias. An approach similar to the one used for self bias can be used with voltage divider bias to graphically determine the Q point of a circuit on the transfer characteristic curve. In a JFET with voltage divider bias, when Id is equal to 0, Vgs is not 0 as in the self biased case, because the voltage divider produces a voltage at the gate independent of the drain current. The voltage divider DC load line is determined as follows. For Id is equal to 0, Vs is equal to Id into Rs and is equal to 0 into Rs and comes out to be 0 volts. Vgs is equal to Vg minus Vs and is equal to Vg minus 0 volt and comes out to be Vg. Therefore, one point on the line is at Id is equal to 0 and Vgs is equal to Vg. For Vgs is equal to 0, Id is equal to Vg minus Vgs over Rs and comes out to be Vg over Rs. A second point on the load line is at Id is equal to Vg over Rs and Vgs is equal to 0. The point at which the load line intersects the transfer characteristic curve is the Q point. Q point stability. Unfortunately, the transfer characteristic of a JFET can differ considerably from one device to another of the same type. If, for example, a 2N5459 JFET is replaced in a given bias circuit with another 2N5459, the transfer characteristic curve can vary greatly as illustrated in this figure. In this case, the maximum IDSS is 16 milliampere and the minimum IDSS is 4 milliampere. Likewise, the maximum VGS off is minus 8 volt and the minimum VGS off is minus 2 volt. This means that if you have a selection of 2N5459s and you randomly pick one out, it can have values anywhere within these ranges. If a self biased DC load line is drawn as illustrated in figure here, the same circuit using a 2N5459 can have a Q point anywhere along the line from Q1 the minimum bias point to Q2 the maximum bias point. Accordingly, the drain current can be any value between ID1 and ID2 as shown by the shaded area. This means that the DC voltage at the drain can have a range of values depending on ID. Also, the gate to source voltage can be any value between VGS1 and VGS2 as indicated. Figure here illustrates Q point stability for a self biased JFET and for a JFET with voltage divider bias. With voltage divider bias, the dependency of ID on the range of Q points is reduced because the slope of the load line is less than for the self bias for a given JFET. Although VGS varies quite a bit for both self bias and voltage divider bias, ID is much more stable with voltage divider bias. Current source bias. Current source bias is a method for increasing the Q point stability of a self biased JFET by making the drain current essentially independent of VGS. This is accomplished by using a constant current source in series with the JFET source as shown in the figure. In this circuit, a BJT acts as a constant current source because its emitter current is essentially constant if VEE is much greater than VBE. A FET can also be used as a constant current source. As you can see in part B of the figure, ID remains constant for any transfer characteristic curve as indicated by the horizontal load line. The ohmic regions. The ohmic region is the portion of the FET characteristic curves in which Ohm's law can be applied. When properly biased in the ohmic region, a JFET exhibits the properties of a variable resistance where the value of resistance is controlled by VGS. After completing this section, you should be able to discuss the ohmic regions on a JFET curve, calculate slope and drain to source resistance, explain how a JFET can be used as a variable resistance, discuss JFET operation with the Q point at the origin and calculate transconductance. As shown on a typical set of curves in figure, the ohmic region extends from the origin of the characteristic curves to the breakpoint of VGS is equal to 0 curve in a roughly parabolic shape. The characteristic curves in this region have a relatively constant slope for small values of ID. The slope of the characteristic curve in the ohmic region is the DC drain to source conductance GDS of the JFET. The JFET as a variable resistance. A JFET can be biased in either the active region or the ohmic region. JFETs are often biased in the ohmic region for use as a voltage controlled variable resistor. The control voltage is VGS and it determines the resistance by varying the Q point. To bias a JFET in the ohmic region, the DC load line must intersect the characteristic curve in the ohmic region as illustrated in this figure. To do this in a way that allows VGS controlling RDS, the DC saturation current is set for a value much less than IDSS, so that the load line intersects most of the characteristic curves in the ohmic region as illustrated. In this case, ID saturation is equal to VDD over RD and is equal to 12 volts divided by 24 ohm and comes out to be 0.5 milliampere. Part B shows the operating region expanded with 3 Q points shown, that is Q0, Q1 and Q2 depending on VGS. As you move along the load line in the ohmic region, the value of RDS varies as the Q point folds successively on curves with different slopes. The Q point is moved along the load line by varying VGS is equal to 0 to VGS is equal to -2 in this case. As this happens, the slope of each successive curve is less than the previous one. A decrease in slope corresponds to less ID and more VDS, which implies an increase in RDS. This change in resistance can be exploited in a number of applications where voltage control of resistance is useful. Q point at the origin. In certain amplifiers, you may want to change the resistance seen by the AC signal without affecting the DC bias in order to control the gain. Sometimes you will see a JFET used as a variable resistance in a circuit where both ID and VDS are set at 0, which means that the Q point is at the origin. A Q point at the origin is achieved by using a capacitor in the drain circuit of the JFET. This makes the DC quantities VDS is equal to 0 and ID is equal to 0 milliampere. So, the only variables are VGS and ID, the AC drain current. At the origin, you have the AC drain current controlled by VGS. As you learned earlier, transconductance is defined as a change in drain current for a given change in gate to source voltage. So, the key factor when you bias at the origin is the transconductance. This figure shows the characteristic curves expanded at the origin. Notice that the ohmic regions extend in the third quadrant. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. We learned that the Q point in a JFET with voltage divider bias is more stable than in a self biased JFET. Current source bias increases the stability of a self biased JFET. A JFET used as a variable resistor is biased in the ohmic region. To bias in the ohmic region, ID must be much smaller than IDSS. The gate voltage controls RDS in the ohmic region, and finally we learned that when a JFET is biased at the origin, the AC channel resistance is controlled by the gate voltage. So, that is it in today's lecture. In the next lecture, we shall talk about the MOSFET characteristics, parameters and its biasing. So, that is it for today. Thank you very much.